Life on this planet has repeatedly nearly been wiped out by huge asteroids crashing through our atmosphere and into the planet's surface. But it seems we may all owe our lives to one of the largest collisions in Earth's history when an embryonic planet similar to Mercury smashed into the Earth. A new study has uncovered evidence that suggests almost all the carbon that forms the basis of life on Earth may have come from this cataclysmic event around 4.4 billion years ago. It suggests the diminutive world around 3,000 miles across merged with our planet after the Earth's core had formed, bringing the ingredients for life and precious crystals like diamonds. But if correct, it suggests that the development of life on this planet was reliant upon this chance collision billions of years ago. Exactly how the Earth's mantle and crust came to have so much carbon in it has puzzled geologists for some time. Most of the carbon on our planet after it first formed would have boiled away or been locked away in the planet's core. Dr. Radeep Dasgupta, a petrologist at Rice University in Houston, Texas, said, "The challenge is to explain the origin of the volatile elements like carbon that remain outside the core in the mantle portion of this planet. We have published several studies that showed even if carbon did not vaporize into space when the planet was largely molten, it would end up in the metallic core of our planet, because the iron-rich alloys there have a strong affinity for carbon. We thought we definitely needed to break away from the conventional core composition of just iron and nickel and carbon." The researchers, whose work is published in the journal Nature Geoscience, conducted experiments under huge pressures to examine how sulfur or silicon might alter the affinity of iron for carbon. It revealed that carbon could be excluded from the core and relegated the mantle, which is largely formed of silicate, if the iron alloys in the core were rich in either silicon or sulfur. When the team mapped out the relative concentrations of carbon that would arise under various levels of sulfur and silicon enrichment and compared them to those found in Earth's mantle, a compelling scenario emerged. Dr. Dasgupta said, "One scenario that explains the carbon-to-sulfur ratio and carbon abundance is that an embryonic planet like Mercury, which had already formed a silicon-rich core, collided with and was absorbed by Earth. Because it's a massive body, the dynamics could work in a way that the core of that planet would go directly to the core of our planet, and the carbon-rich mantle would mix with Earth's mantle." In this paper, we focused on carbon and sulfur. Much more work will need to be done to reconcile all of the volatile elements, but at least in terms of the carbon-sulfur abundances and the carbon-sulfur ratio, we find this scenario could explain Earth's present carbon and sulfur budgets. The findings fit with another theory that suggests our moon formed around 4.5 billion years ago after a planet called Theia collided with Earth. Many scientists have also suggested that life itself, or at least the complex ingredients such as water and amino acids, were brought to Earth from outer space on asteroids and comets. But the new findings suggest that we owe our existence to a much greater collision in the past. Dr. Yuan Li, lead author of the new study and a geochemist at the Chinese Academy of Sciences, said, "One popular idea has been that volatile elements like carbon, sulfur, nitrogen and hydrogen were added after Earth's core finished forming. Any of those elements that fell to Earth in meteorites and comets more than about 100 million years after the solar system formed could have avoided the intense heat of the magma ocean that covered Earth up to that point. The problem with that idea is that while it can account for the abundance of many of these elements, there are no known meteorites that would produce the ratio of volatile elements in the silicate portion of our planet,